All right. Hi, everybody. Welcome back. Okay. This part here, we're going to look at the central limit theorem. So the central limit theorem says uh, if you have a population with a mean and a standard deviation, which we do, we just proved it over here in Excel that we have a die has a mean and a standard deviation, and you do that a bunch of times, and and it says random samples from the population with replacement. What replacement means is that essentially when you pick a value, you put it back into the population. You keep doing that over and over again. That replacement is important, but just remember in central limit theorem, when you pick something out, you put it back into population. So central limit theorem says that when you do this a whole bunch of times, it's going to start to look like a normal distribution, even if it's not originally a normal distribution. So I'm going to show you how central limit theorem and rolling the dice a bunch of different times in Excel, we can go from a not a normal distribution to all of a sudden a beautifully normal distribution. So let's look at that. So we don't need any additional Excel functions because these all apply. So the first thing I'm going to do is I'm going to set it up. So here I have that we're doing rolls. For this particular case, I went ahead and did the 5,000 cases. And then I did the RAND between 5,000 and 1. And here we have, so each sample for us is that, imagine that you rolled 6 die together and you counted up all the values and you summed it up. So the first thing I want to draw your attention to is that I have 6 rows of 5,000 values, which is 30,000 values. So already, hopefully, you can kind of understand the power of the Monte Carlo simulation is I'm proving a point using 30,000 numbers. And I can just kind of re-roll the die anytime I want and prove the same point and see that things don't really change all that much from roll to roll. I mean, the shape kind of moves around a bit, but the overall results are roughly the same. And this is the power of simulation in general. So a couple of other things to keep in mind. So here we have the only results that we care about really are the sum of all the numbers. We're rolling 6 die. So what does that mean? Well, it means that the smallest number that we can roll when they're all added together is 6. Imagine you rolled a 1 on each die, and the highest number that we could roll is a 36. Imagine we rolled all 6s on each die. So 6 times 1 is 6, 6 times 36, 6 times 6 is 36, and somewhere in between we have all the other values. Okay. So now if you remember, we had 1 die, and we had the average, the variance, and the standard deviation. And it turns out, and you can again look this up, that that you can figure out the mean of when you're adding in numbers together just by adding all the numbers together and getting a new mean. So means are additive, and so is a variance. And that is something you can look at over here. Here's a function that I looked at. I looked it up on Wikipedia, variance. And without doing all the math, you can see here, somebody else already told me that, variance plus xy is equal to variance x plus variance y. Okay, so how does that apply here? Well, we took a 6-sided die and we rolled it 6 times. So the average mean is going to be 6 times the average of 1 die. So the mean here was 3.5, and this one then is 6 times 3.5. Variance too. We rolled 6 die, and there's a variance associated with 1 die. And so 6 times that variance is, in this case, 17.5. So we went from a variance 2.9 to 17.5. And then the standard deviation is the square root of the variance. That's just the definition. Okay, so then that means that when we roll die, we expect to see the average as 21 and a standard deviation of 41.8. There's another concept that I want to remind you of and this is kind of related to the standard deviation, but in statistics, it's commonly known that 68% of the numbers are within one standard deviation, 95% are within two standard deviation, 99.7% are within three standard deviations, when it's a normally distributed population. And you can look up this rule here in Wikipedia. I left it there. So you can kind of see that, you know, I put it above this chart just so you had a visual anchor. But 68% is 68% plus minus from the mean, which means it's 34% on one side, 34% on the other. 95% for 2 sigma means, you know, half a 95 to the left, half a 95 to the right, and 99.7%. Incidentally, I want to say that, you know, 6 sigma, which I'm sure you have all heard about, comes from this right here, and 6 sigma then I think is like 99.000 or 99.999999. I think it's like 1 error per million or something is what the 6 sigma was. I have to look it up. I don't really know, but interestingly enough, that is where the term came from. So in this exercise here, what I wanted to do was look at what are the values for 1 standard deviation, 2, and 3 sigma. And that is actually easy to do because we have our standard deviation from this handy table right here. Now we have the mean minus a standard deviation. So we have the minimum value then is around 16, and the maximum value is around 25. And then to be within 2 sigma of the mean, or at 95%, the dies are going to be between roughly 12 and 30. And then to be within 3 sigma, we're going to be between 8 and 33. Okay, let's see how this works. We rolled the die 30,000 times, and we did our math. So the first thing I'm going to do is I'm going to go ahead and create a chart from 6 to 36. And all we're going to do is count the number of times something happened. And this is going to be pretty simple. We have our range of values that we're looking from, which remember I said the only thing we care about is this column right here. And I'm going to count. If the numbers in this range, tell me how many numbers in this range equal to this cell value. And again, I apologize for the syntax. It's not mine. It's the way Excel makes you do things. In order to say equals a cell, you have to say equals in quotes, and then you do and the cell number. It's ugly, but that is the way that you do it. And so I went through these 5,000 values, and I just made a table. And I said, hey, how many times did I roll a 6? 0. How many times did I roll a 7? 0. How many times did I roll a 17? 310, etc. And I just counted. And down here, I add them all up, and sure enough, it all adds to 5,000. To come up with the probability of each number, I just take the number of times the number appeared, and I divide it by the number of rolls that I did. Sorry, the number of samples that I did, which was 5,000, right? So here we have a chart. And then the other thing that I did is I then took all these probabilities and added them up to find out where it would be at any given time. So let's look at these values here now then. So the first thing I did is I plotted a histogram of, I plotted a histogram of these values right here. And so you can see that, we got roughly 400-ish, 490, 478 points of 21. If you come over here, you can see it of 22. Sorry, right there. So what I want you to notice here is the shape of the curve. This is a normal distribution shape. And what's powerful is that we went from one die being rolled, which has a flat number, and when you do a bunch of them, when you do 6 of them, 5,000 times, or 30,000 total, look at this, you get a normal distribution, right? So I could plot the count here, which I did. I could plot the count is plotted here. I could plot the distribution, the probability distribution, which is just plotting this number. And you'll note that it looks exactly the same as this distribution here, which makes sense because all I did is took these values, divided it by 5,000. So it looks exactly the same. And what's really neat is I get this plot of cumulative probability. So I can find out any point in time, like, what's the probability that I roll a number higher than 16? Well, it's the area under the curve here says that I get 14% at 16. And so the probability of rolling 16 or lower is 14%. The probability of rolling 16 or higher then is going to be the opposite value, which is 1 minus 14, or it's going to be 86%. So this is essentially how you do Monte Carlo simulations and how you do some of the analysis. So now let's actually go deeper in. Remember, we looked at this expected value curve here, and we said, hey, here's the mean. Here's the standard deviation. And I went through and I calculated the min and max at 1 sigma, 2, and 3 sigma. Let's see what really happened in our actual simulation. So I took the average of all of these 5,000 values. We expected 21. We got 21.05. Not bad. Standard deviation, 14.18. We got 14.17. Okay, now here's where we use the percentile values. And this is kind of where you need to follow me a little bit of what the 1 sigma means, 2 sigma and 3 sigma, that it is 68% around the middle, around the mean, or 95% around the mean. So in calculating the percentile here, the range of numbers that I wanted to look at is the same range of numbers that I've looked at, all 5,000 of these. And then I want 68% around the mean. So I take 50%, which is 0.5, and I subtract out 68% divided by 2, which is the percentage then that I want is actually, what is it, 0.5 minus 0.68 divided by 2. So I want the 16th percentile. So that's just using this percentile function. I say, hey, give me the 16th percentile of this range of values, and then give me it's this here. Instead of going minus, I'm going to go plus. Here we have the 84th percentile, and that's 25. And this is of the data that we collected. So the neat thing about this percentile function is that you don't have to sort the numbers beforehand. You can just give it the raw data, and it figures out, it sorts it, and it figures all that out for you, which is really neat. So look here. In our 5,000 samples consisting of 30,000 rolls of the dice, we expected that our within 1 sigma that we would get between 16 and 25. I'm going to go ahead and increase the value on this. Well, they're integers, I guess, so that they're solid numbers. So within 1 sigma, in our real data, we're at 17 and 25, which matches this. We expected to be at 16.8, which is 17. We expected to be at 25.18, which is 25. Here, we expected to be at, rounding up, 13, and rounding down, 29. 13, 29. Look at that. Here, 84.5. Rounding up, we're at 9. Rounding down here, 33.5, and we're at 33. So look at that. We just did 5,000 rolls, and we didn't worry about any theory at all. We just simply said, hey, Excel, tell me what these percentages should be, and we matched theory. So this is kind of the power of Monte Carlo simulation. We're going to look at how it applies to investments in a minute, but I just wanted to show you Monte Carlo so you had a good understanding of how that works. There's something else that you can do here as well. I just wanted to say, like, what's the probability that we have a number that's greater than or equal to the mean, or less than or equal to the mean? And because this is a normal distribution, we expect half of it to be above and half of it to be below. So There's a little bit of a problem here, though, in that from the way COUNTIF works, if I did greater than equal to of one of these numbers, and then for the other numbers I did less than or equal to, I'm going to double count all of the numbers right in the middle. So I did for greater than or equal to the average, I put the mean right at the middle. And so you see we have 55% are the mean or higher, and 45% are the mean or lower. When you add them together, I get 100. And if we look real quick, the mean is K14, which is 21. So 55% of the numbers are 21 or higher, and 45% of the numbers are lower than 21, right? But it turns out it's actually pretty easy to get 50-50 and do the greater than or less than, greater than or equal to or less than or equal to, if I just take this middle number, the 21, and I split it in half. So I give half of the count to one side and half of the count to the other side. And when I do that, which is a little bit more complicated of a formula, and you can see it here when you look at the Excel spreadsheet, look at this. I get 50% of the numbers were greater than the average, and 50% of the numbers were less than or equal to the average. And that's pretty cool, because that's exactly where you expect the average to be, right in the middle. And again, all of this right here was done numerically. All I did is do a bunch of random things and count. And that was it. And that's the power of the Monte Carlo method. So next, we're going to look at solving the stochastic solution using the Monte Carlo methods. See you in a couple of minutes.